We're continuing our discussion of inverses, inverse functions. State where the function has an inverse. If yes, find it. If no, restrict the domain so it does have an inverse. This idea right now is more of an advanced idea that I dealt with on the last class as well for restricting the domain. Our book won't ask you to do that, but it is a good thought to be able to do and think about what's going on in the problem. Let's take a look at this. Does this have an inverse? This isn't such an easy question to ask. What's going on with this problem? We need to think about this a little bit, and I don't have a concrete way that you could say, oh, this is a way you're going to proceed here. You have a cubic term in here. There are no even powers. Just with the odd, it's possible that it has an inverse, and it's possible it doesn't have an inverse. Let's kind of think about what's going on. If you cube a number, is it possible to cube two different numbers and get the same result? For example, can I cube 1 cubed, okay, and I get 1. Is there any other number I could cube that I would get 1? What if it was -1 cubed? That I get -1. If I cube a positive number, it's always positive. If I cube a negative number, it's always negative. Unlike if I was squaring a number, if you squared a positive or negative, if the numbers were the same, then you're going to get the same result. But here, if I cube it, I don't get the same result, and there's no way to cube two different values and get the same result. Now let's look, what if I take all of those numbers and add 1? Well, I still have different numbers for each one. What happens when you take a cube root? You're looking what number multiplied by itself 3 times gives me the original. Is it possible to cube root two different numbers and get the same result? No. This does have an inverse. And so we have y equals cube root of 1 plus x cubed. X equals cube root of 1 plus y cubed. Now we want to solve for y, so we're going to cube both sides. Remember, a cube root's the same as a 1/3 power. So we're going to raise this to the 3rd power. We'll get x cubed equals 1 plus y cubed. Move that 1 to the other side. Take the cube root, again, same as 1/3 power. Do we have a plus or minus when we're taking an odd root? No. Why? Because a number multiplied by itself 3 times is going to be either positive or negative, whereas the square root, when you have an x squared, if you square a positive or negative, you still get a positive answer. And then we're going to change our y back to, or into f inverse. So we have f inverse equals the cube root of x cubed minus 3. And that's it there. Let's take a look at this. This is a great problem to take a look at review. Let's first start with the domain. How am I going to find the domain of this thing? Well, this is a square root. Remember, we're either looking at domain or the values that work or the values that don't work. In a square root, what can you take the square root of and still get a real answer, a real number for the answer? It's either 0 or positive. So what we're going to do is say 4 minus x squared is greater than or equal to 0. Now this brings us back to chapter 3 where we are solving polynomial inequalities. We factor this. Remember that next step, we're going to do a number line. So we have our zeros at plus or minus 2. And we're going to sketch this graph. The degree is 2, and is it positive or negative? It's a negative x squared, so it's negative, so I'll go an upside down parabola. This part's negative, positive, negative. What do we want? We want the positives or 0. So our domain here would be from -2 to 2. Now, if I plug in -2 or 2, what does this graph look? What happens there? So if I say f of -2, it's going to be 4 minus 4. Square root of 0 is 0. F of 2 equals 4 minus 4. Square root of 0 is 0. Does this have an inverse? No. Do you know what this graph looks like? We could plot points. We could plug in a bunch of values like 1, 0. This thing is looking like this. It's a semicircle. Now, thinking back what we did in the last lesson, we had, does this have an inverse? No, it doesn't. Why doesn't it have an inverse? Because it's not a one-to-one function. It does not pass the horizontal line test. So we're going to restrict it to make it a function. So what side do you want to restrict it to? Just for the sake of simplicity, I'd say let's just go with the right side. So we will restrict the domain to x such that we're between 0 and 2 inclusive. What's our range values there? Is our domain. Our range will be y such that y is between 0 to 2 as well. And you can see that here. If I'm going 0 to 2 there, the y values are going 0 to 2. So now let's find our inverse. And we get y equals square root 4 minus x squared. X equals square root 4 minus y squared. Square both sides. X squared equals 4 minus y squared. Move the y to the left side and the x squared to the right side. So we'll get y squared equals 4 minus x squared. Take the square root, put our plus or minus down. Y equals plus or minus 4 minus x squared. Now which one do we want? We need to look again at what did we restrict it to. We restricted it to the positive side. Here's our domain and range of the original, and they happen to be the same. So for our inverse function, they're also going to be the same. So we want 0 to 2. So what we want to do is get rid of that negative. F inverse of x will be square root of 4 minus x squared. Now what do you notice about that? The inverse is the same as the function itself. Why? Let's take a look. It's just this piece. Remember, the inverse is a reflection about the line y equals x. Well, what happens when you reflect this graph about that line? Both halves are the same thing. So it is its own inverse. Now, what if we put our domain from -2 to 0? What would our range be if we just cut off the right-hand side? Our range would still be from 0 to 2. And this is for f of x. That means for f inverse of x, since our domain and range are switched, since x and y are switched, we will have the domain will be from 0 to 2, but the range will be from -2 to 0. So on this one, when I find my inverse here, and I've already done all the work there, which one would I want? Would I want the positive or the negative? Well, my range is going to be the negative values, so I would have negative of 4 minus x squared. And what would that look like? This would be the original f of x, and the reflection about that line would be this bottom part here. And that would be the graph of negative square root 4 minus x squared with these restrictions. All right, let's take a look at number 2. Find H inverse. Now this one's going to be a little bit harder. There's a little bit more algebra we need to do on this. So we have y equals, let me just kind of section this off. Y equals x over x minus 1. And we'll switch x and y. Now how are we going to solve that equation? We need to get y by itself. So let's multiply both sides by y minus 1, and we'll have xy minus x equals y. Let's move the x's to one side and the y's to the other side. I'm going to move the y to this side and the x to this side. Now I got this problem because I have xy there, but my goal here is to solve for y. I need to get one y in there. I need to get y all by itself. It needs to be isolated. So when I get it now, what do you think I can do? I just need one y. I can't have two. What mathematical idea could I apply to this so I would only have one y written down? I could factor. Now if I divide by x minus 1, we get, in this case it's not an f, it's h. H inverse of x is going to equal x over x minus 1. Now, what strikes you about this one? Once again, I gave you an example where the inverse was the exact same thing as the original function. It doesn't always work out that way. Now, this is as far as sketching this graph, for where we're at right now, I would say it'd be perfectly okay to use the calculator. I'll show you what this graph looks like. It has a vertical asymptote at 1. And what's going to happen in this graph, it's going to have a horizontal. We haven't talked about this, and I don't expect you to know this, but the graph is going to look like this. So now if I put in that y equals x graph, you can see that it is again a reflection about itself. I wanted to do a review problem in terms of finding symmetries. What you want to do is you want to recognize immediately when you have these four symmetries to what are you going to plug in to check for it. Remember, what we are dealing with in an inverse function, which is a reflection, we're dealing with two different graphs. We have our original one and we have the inverse, which is a reflection about y equals x. When you're talking about symmetries, on the other hand, you only have one function, or one equation, I should say, because it's not necessarily a function. So what are we going to test when we're testing for the x-axis? What point are we plugging in? What general point? It's going to be x comma negative y. And so if we plug this in, we'll have absolute value of x times negative y equals 12. And then this is negative xy, absolute value. And what's the absolute value? What effect does that negative have in the absolute value? None. This is equal to the absolute value of xy equals 12. So yes, this is symmetric about the x-axis. The y-axis. On this one we plug in negative x comma y. So we have negative x times y. And the absolute value of that will just be xy. And that's also true. What are we plugging in for the origin? We have negative x comma negative y. Negative x times negative y. Is that true? We have xy equals 12. Yes, once again, that is also true. Y equals x. We have y times x. Yes, that's the same as xy equals 12. So in other words, this thing is symmetric about the x-axis, y-axis, origin, and y equals x. One way to kind of get going on this is let's graph part of this graph just in the first quadrant. So let's plot some points in that first quadrant only. If I plug in a number like 1, I get 12. If I plug, so right now I just want to look at xy equals 12, or in other words, y equals 12 over x. If I plug in 2, I get 6, 3 is 4, 4 is 3, 6 is 2, 12 is 1. So let's take a look. 1 is going to be all the way up here at 12. 2 will be at 6. 3 will be at 4. 4 will be at 3. 6 is at 2. and then 12 is at 1. So if I look at this and I connect these dots, I get this. Now, this is symmetric about the x-axis. So let's reflect these points over on the other side of the x-axis. So I will have a point there, and then here, and then that one there. I'll go here. So notice what I'm doing here. I'm just copying these points on the other side. But I think I copied them. I didn't put them at the right level, did I? Let's try that again. So 6 is at 1 unit, or it's at the value of 2. And then 4 is at 3, so this will be at -3. And then 3 is at 4, so it would also be at -4. And then 2 is at 6, or -6. And then 1 is at 12, or -12. So we have this piece. Now let's use the next one. Y equals the y-axis. That means we're going to take, the whole graph is symmetric about the y-axis. We're going to take this and we're going to flip it over the y-axis. So now we have a point here. We have -1, 12, -2, 6, -3, 4, -4, 3, -6, 2, and -12, 1. And we also have to flip this side, this in the fourth quadrant, over to the third quadrant. And also, if we had started, let's say we had started first with the y-axis and we reflected that over because it's symmetric about the x-axis, that's also going to be true. And at this point, we can go a little bit quicker on there. So we have those values. And then this one would be at -3, -4. Now, I didn't use the origin. The origin is taking all of our points here and it's basically rotating them 180 degrees about the origin. That works. And if I look at this graph and I reflect it about the line y equals x, both halves match up. So here's a graph that is symmetric about the x-axis, y-axis, origin, and y equals x. We tested for all of our symmetries and sketched its graph. Actually, no, not sketched. We graphed it. And that's it.